See, under this Planck's quantum theory, second point is energy present in each quantum is given by E is equal to h nu. E is equal to h nu. Okay, and what is nu? Nu we know it is frequency. And h is Planck's constant. Planck's constant, and its value you should remember 6.625 into 10 raised to minus 34 to 10 raised to minus 34 joule second. Okay, so that is the value for solving problems and all. H value to remember 30. So energy present in each quantum is given by E is equal to h nu. Now nu expression C is equal to nu lambda, and nu is equal to C by lambda. All those things you can write, not a problem. Okay, next. When some object emits quantum or absorbs quantum, he says only integer multiple of quantum is emitted. I'm sorry, it's got crashed. Sometimes the app becomes non-responsive. Now internet connectivity has become a problem nowadays. Even in the broadband, they say 100 Mbps, but it doesn't come to even 15 Mbps at peak hours, because everybody are using internet nowadays. Okay. Only integer multiple of quantum is emitted or absorbed by an object. That's the meaning. Okay, that means E is equal to n into h nu, where n is integer. It starts from 1, 2, 3, etc. It goes, and n can't be fraction. N is not equal to fraction. That means half a packet of energy will never be emitted. Only integer multiple of quantum will be emitted. What is one important thing you should know? In case of light, the quantum is referred as, quantum is a small packet of energy, is equal to photon. We say photon. Energy present in each photon is equal to E is equal to h nu, like that. This is the concept of, okay, Planck's quantum theory. So Maxwell imagined the light as the one which has electric field and magnetic field component perpendicular to each other, and also perpendicular to the direction of propagation. Like that, Max Planck has assumed the light to be emitted or absorbed in terms of small packets of energy. These are all the theories which has been proposed at times to explain certain properties observed, experimentally. Okay, so the radiation will have its own properties. See, radiation found to be deflected by external magnetic field and electric field. Then Maxwell concluded that, oh, light also must have electric field component and magnetic field component, like that. Similarly, in order to explain certain phenomena like photoelectric effect and all, this Planck's quantum theory is also used. Okay, so this is about different concepts of light. Okay, so let's proceed. Yes.
Sir, can you just go back to the previous
Oh,
slide?
fine. Is it down?
Yes, sir.
Yeah.
Sir, still down, sir.
Yeah, you can go. only integer multiple of quantum is emitted or absorbed. Shall I proceed?
Yes, sir.
Next, so we'll take up photoelectric effect. Photoelectric effect. So what is photoelectric effect? Let's see now. Okay. Now you take any metal, okay, and just expose the metal to the radiation, different radiations, to the sunlight. Okay. What is observed is when light radiation fall. Okay. So you expose the metal. Metal, when I say, it may be sodium, magnesium, calcium, iron, or any metal for that matter. You expose it to the sunlight. The light radiation fall onto the metal surface. And sometimes it is observed that when light radiation fall onto the metal surface, electrons are emitted like this. Light radiation of energy h nu, when falls on a metal surface, electron will be emitted. Now, is it like all the radiation which fall onto the metal surface eject the electron from the metal surface? No. All the radiation would not emit or remove the electron from the metal surface. Then which radiation will remove the electron? Certain radiation of a particular energy. And energy is given by E is equal to h nu. We know that. So energy. So a particular energy of radiation when falls onto the metal surface, electron are removed from the metal surface, because metals contain electrons. Metals always found contain free electrons in it everywhere. Okay. This is metal. Now, what is that particular energy radiation which removes the electron called? That is called threshold energy. Okay. So what should be the energy of the radiation? E, energy should be threshold energy. We give the symbol E naught. That naught is written for threshold energy. Okay. So E is energy of the radiation. Any energy. What is E naught when I say? E naught is threshold energy. What is threshold energy? It is the minimum energy required to remove electron. Okay, the minimum energy required to remove electron is called threshold energy. So E naught is equal to h nu naught. I can write. What is nu naught then? Nu naught is called threshold frequency. What is threshold frequency? It is the minimum frequency of the radiation required to remove the electron. Anything similar definition you can. Okay. Now I'll revisit the definition. What is photoelectric effect? It is the phenomenon of ejection of electron from a metal surface when a radiation of suitable frequency incidents on it. It is the phenomenon of ejection of electron from a metal surface when a radiation of suitable frequency incidents on it. What is that suitable frequency called? Threshold frequency. The energy corresponding to the threshold frequency is called threshold energy. Is that okay? So how do we
Sir,
deal
can
with
you
it?
repeat?
The phenomenon of ejection of electron, phenomenon of ejection of electron from a metal surface when a radiation of suitable frequency incidents on it. Okay, that is what is the photoelectric effect. And these electrons which are removed are called photoelectrons. The electrons which are removed are called photoelectrons. This is the metal surface. Okay. Now I can give mathematical expression like this. What is that? See, let us say some radiation of energy E is incidenting on the metal surface. Some energy E, that energy is greater than threshold energy. Okay, so E is equal to some part of energy will be used to remove electron. How much energy is required to remove electron? Threshold energy E naught. Okay, then the remaining amount of energy will be transformed into kinetic energy. Okay, let's say we didn't understand the statement. Let's say in order to remove the electron from the metal surface, it requires, let's say, around say 10 joules. So what is 10 joules? 10 joule is the minimum energy required to remove the electron from the metal surface. So what is it called as? Therefore 10 joules can be called as threshold energy E naught. So if some radiation of exactly 10 joules incident on the metal surface, electron is just removed, that's all. Just removed from the metal surface. Now let's say there is a radiation of energy 15 joules incidents on the metal surface. Now this 15 joule energy, can it be called as threshold energy or energy greater than threshold energy?
Greater than threshold energy.
Greater than
So, greater than threshold energy. What happens? 10 joules will be used for removing electron. Remaining 5 joules is there now. That will be transformed into kinetic energy of electron, with which electron removed moves with a certain kinetic energy. So plus 5 joules. This is threshold energy. And this 5 joules will be imparted as kinetic energy of electron. Is that okay? So this is how things happen. Okay. So if, let's say, if there is a radiation with 8 joules incidents on the metal surface, excuse me, what would happen?
Sir, two joules of kinetic energy should be added.
No, what would happen if a radiation of 8 joule incidents on the metal surface?
Sir,
Electrons
electron
will
will not be moved, sir.
Nothing happens. That means no photoelectric effect observed. Photoelectric effect observed. No photoelectric effect. What happens if exactly 10 joules incident on the metal surface? Electron is just removed. Just removed. What happens? Energy of the radiation, if it is incidenting on the metal surface, is greater than threshold energy, then how much ever excess energy is there, that will be imparted to the electron as kinetic energy, with which the electron starts moving. Okay, electron is not only removed from the metal surface, then electron starts also moving away from the metal surface. Okay, so that's why E here I have written in the green. E is the energy of the incident radiation. If that energy is greater than threshold energy, then a part of energy is used for removing electron, which is nothing but E naught. The remaining part of energy will be imparted to the electron as kinetic energy. So I can write energy of the incident radiation. Energy of incident radiation E is equal to E naught plus kinetic energy. Okay. So what is E naught? E naught is threshold energy.
Sir, I have a doubt.
Ah,
Sir, you told the energy that is like the photon. The photon will hit the electron so that it will like emit radiation. But photon has no mass, sir. So how will it?
that is where exactly light is concluded as the particle in nature. Light can exhibit particle nature also. That is where exactly this point has triggered the discussion of particle nature of light. Okay. So
Sir, but it has no mass, sir. How can it?
exactly, that's how exactly this is the experimental evidence for concluding light as the particle in nature. See, that's how. Let's say there is an object here. Let's say there is one marble I have kept here, or a chalk piece. One person is holding another chalk piece, okay, and throwing it in. So when chalk piece hits another chalk piece, so what would happen? Energy will be transformed. Chalk piece starts moving. Whereas when a wave hits the object, it will only reflect back. Light exhibit both. You know, when a light hits the object, it can bounce back. It will be
Sir,
reflected.
but it has no mass, sir. It's like throwing the chalk piece with nothing.
Exactly. That is the reference which is used to conclude light as particle in nature also. Light can behave like a particle despite of not having mass. That is the speciality of light. Is that okay? This itself is the proof. That's what I told you last time while explaining dual nature. Photoelectric effect becomes a direct evidence for particle nature of light. Light can behave like both wave and particle. The speciality is lies in it is not having mass, yet it can behave like a particle. That is the theory. The theory what it concludes. Okay, electron is a particle with some mass. When light incident on that, if electron is ejecting out of the metal surface, light must be behaving not just as wave, it must be behaving like a particle also. That is the conclusion. Light can behave a particle as well as wave. That is duality of light, we say. Despite of not having mass, it can still behave like a wave. Later we are going to see dual nature of matter also. What is dual nature of matter? Any material particle having some mass can behave like wave also. That is what the gift given by the nature. For a particle there is wave nature also. For light without having mass there is particle nature also. That's how duality exists in the nature. Light is dual, material particle is also dual. That is how entire quantum mechanics is developed. Is that okay? So later this duality becomes a reality. Anything you take, there is duality. Material particle you take, there is particle nature and wave nature. Light you take, there is wave nature and particle nature. So that is what exactly the conclusion is. Okay. Here we are only taking the summary of the entire photoelectric effect. Later, when it comes to physics, they are going to deal with it in complete detail, Einstein's explanation and everything. So just you need to understand what is photoelectric effect and the atomic structure now. Okay, let's take a further. I was telling this energy of the incident radiation E is equal to, it will have two parts. A part of it will be used to remove electron and remaining part will be imparted to the electron as kinetic energy. Okay. Now, E is nothing but H nu. E naught is nothing, sorry, H nu. E naught is nothing but h nu naught. Kinetic energy is half mv square is the expression for kinetic energy. Okay, so just know about it. Sometimes there may be problems on this. And also they call this E naught as work function. Different terminologies are used. Work function is the minimum energy required to remove the electron from the metal surface. Is that okay? So later, see, this phenomenon was first observed. Later, Einstein gave the explanation for photoelectric effect using Planck's quantum theory. Incident radiation will have some energy h nu. A part of energy is absorbed by to remove the electron. Remaining part of energy is imparted to the electron as kinetic energy. So this is basically Einstein explanation. Now graphically,
Can you explain once again, sir, that h nu equals h naught?
what is as per Planck's quantum theory, what is the energy present in each packet of quantum? E is equal to h nu. So in that way, energy of the incident radiation is E, correct? E
Yes,
is
sir.
equal to what? H nu. Therefore, what is E naught? E naught is H nu naught. Nu naught is threshold frequency. Expression for
Yes, sir.
kinetic energy of a particle is given by half mv square, where m is mass of electron, v is velocity of the electron. Okay, let me write that. So here nu is frequency. This is nu naught is threshold frequency. When I say this simply nu is the incident frequency. Incident frequency. M is mass of electron. V is velocity of electron. And that overall expression is kinetic energy is given by half mv square, mass of electron, velocity of electron. Okay, that is the expression for photoelectric effect. Graphically, when you take up this, see, this is the kinetic energy along y-axis. This is the incident energy of the radiation. A graph will not be obtained from the zero origin. It will not be obtained from here. So a graph will be obtained after a certain frequency. It starts from here. So let's say this point is the threshold energy E naught. So the incident radiation has to have this much energy to remove the electron from the metal surface. Okay. So as energy of the incident radiation further increases, the energy of the emitted electron, kinetic energy of the emitted electron also increases. That's why a graph will be obtained in this manner. So this is not smooth graph. Let me remove this. Okay, a graph will be obtained. Okay, so what does it mean? At this point, E naught, the electron is just removed with that much amount of energy. If energy of the incident radiation further increases, the electron removed will move like a particle with certain kinetic energy here. Okay, it moves with certain amount of kinetic energy. That's the way. Okay, this is graphically representing the photoelectric effect phenomenon. Is that okay? So let's proceed. See, these are all the concepts which we use in application of Bohr's theory. That is important for us. Next, we'll take up the concept of spectrum. Now, people have to tell me, what is spectrum? What do you mean by spectrum?
Color.
Seven
Band
colors.
of 7 colors.
Sir,
Colors.
the arrangement of the light according to their wavelength.
Separation of light when passed through prism.
Okay. Separation of different components of radiation when a white light is passed through the prism is dispersion. After dispersion, what you obtain at the end is what is spectrum. So spectrum, for example, visible spectrum is Vibgayar, we say. Correct? No? Rainbow of colors, Prajwal says. So visible spectrum has 7 colors. Those 7 colors is the pattern of radiations obtained by arranging radiations in a particular order of their wavelength. So from violet to red, Vibgayar, wavelength increases. Violet to red, wavelength increases. So that is the pattern of radiation. Vibgayar is the spectrum we call visible spectrum, in which different radiations have been arranged in the increasing order of their wavelength. Let me write this visible spectrum. Is the visible spectrum. In this visible spectrum, so from violet to red, when we move here, the wavelength increases. So there is a pattern here where different radiations have been arranged in the increasing order of their wavelength. So that is what is visible spectrum we have. Is that okay? Now, so we give the definition like this: the pattern of radiations obtained by arranging different radiations in the increasing order of their wavelength. Or you can also view it as decreasing order of wavelength, would not be a problem. There should be a pattern, that's all. Decreasing order of their wavelength. Increasing order. So that is what is spectrum. How do you get a spectrum? By dispersion phenomena, correct? No? By dispersion. What you need to do? You need to take a prism, okay, and you need to pass some ray of light into
Sir,
that.
can you scroll up, sir?
Pardon me?
Sir, can you scroll up, sir?
Yeah, please.
Yes, sir.
Right. How do you get spectrum? By the process of dispersion. So how do you do dispersion here? So this is light source, let's say, and it is emitting radiation in all the direction. We need to narrow a beam of radiation onto the prism. So for that, we use slit. So light will now fall onto the prism like this. Okay. Then it starts getting separated from the first phase of the prism itself, like this. Get separated, and again for the separation widens here. So this is prism. Now, in order to observe this, whatever the spectrum obtained, we can either use spectroscope. Spectroscope is the instrument to observe the spectrum, or you can incident all these radiations obtained on a photographic plate. Okay, on a photographic plate, then you will have some kind of impressions on the photographic plate. Okay, that will be called as spectrum. This is what is spectrum. Okay, you need to mention the direction here with arrow marks. This is the direction in which it is moving like this. Okay. So whatever you get the pattern of radiation on the photography plate can be called as spectrum. Okay, then this entire phenomenon is what is separation of radiation in a composite light. This light which is from the source has all the wavelengths in it, composite light. When it is passed through the prism, the wavelengths will be get separated to give spectrum. This phenomenon is called dispersion. Dispersion. Okay, no problem. Next, we need to know something about electromagnetic spectrum. Electromagnetic spectrum. What is electromagnetic spectrum? See, in the nature, there are many radiations. As I told you, X-rays, cosmic rays, gamma rays, microwaves, radio waves, and visible radiation. Of all the different radiations existing in the nature, a small part of it is what we can see by naked eye. Remaining vast majority, vast portion of the radiations in the nature, we can't observe by naked eye. If you arrange all radiations in the nature in a particular order of their wavelength, then you get the electromagnetic spectrum. Okay, so electromagnetic spectrum is the pattern of radiations, electromagnetic radiations in the increasing order of their wavelengths. Okay, so if you arrange all the radiations in the nature in the increasing order of their wavelengths, then whatever you get is electromagnetic spectrum, and that electromagnetic spectrum has all the different radiations. No, you better remember through this word R MeWux gamma C, like that. Remember this as some name of a scientist also. From R MeWux gamma C, as you move from this to this, okay, each letter represent there a radiation. R for radio waves, M for microwaves, I for infrared, V for visible, U for ultraviolet, X-rays, gamma rays, cosmic rays. But the thing is, this is in the decreasing order of wavelength. Radio waves to cosmic waves, radio wavelength decreases. If wavelength decreases, frequency increases because they are inversely proportional. Okay, so you can write now. Come on. First, cosmic ray. Let us go in the reverse order for increasing wavelength. Cosmic ray. After that, gamma rays.
Gamma rays.
Then X-rays.
X-rays.
Next, ultraviolet.
Ultraviolet rays.
Next, visible.
Visible rays.
Next,
Incident rays.
infrared. After infrared, microwaves. Next, radio. Radio waves, like this. Okay, so when you move from this cosmic to finally radio waves, it is increasing order of the wavelength. Wavelength lambda increases and frequency decreases. And this entire range is called electromagnetic spectrum. And you see this visible radiation, the radiation which can be seen by naked eye, is a small portion of this entire electromagnetic spectrum. In the nature, all these radiations exist. How about we people, if we could see all the radiations in the nature, probably we would have understood the universe much better. With whatever little radiation we can see, we are going to have so many inventions and scientific activity. So if you could see all the radiation, probably you would have understood the universe much better. Here is a question by Mohita. Or gamma, that is. Probably you're asking for this. This is gamma.
Sir, what is that last phrase, sir?
Radio wave, microwave. There was no space, that's why I've written a little small. R for radio, R-A-D-I-O, radio wave.
Thank you, sir.
Okay, no problem. So I'll proceed now. See, this small portion of electromagnetic spectrum, which can be seen by naked eye, has the wavelength limit this much. Just need to remember this. From here, 400 nanometer to around 760 nanometer. Okay, the radiation whose wavelength ranges from 400 nanometer to 760 nanometer can only be seen by naked eye, lambda. Okay, any radiation beyond these two limits can't be seen. Okay, there are books which can give 380 to 760, or certain books that also give rounded off figures 400 to 800. No problem. This is said to be something called continuous spectrum. So that's why that kind of disparity will be there. It is approximate value. You just need to remember 400 to 760 or 400 to 800. No problem. Okay. So any radiation whose wavelength lies between 400 to 760 nanometer can be seen by naked eye. Beyond these two limits, we can't see. That's the limit. Okay. So a very small portion of the entire electromagnetic spectrum can be seen by naked eye. Rest everything we can't see. Okay. So this is the thing. Next, we'll take up types of spectrum. Types of spectrum. So spectrum is the pattern of radiation obtained by arranging the radiations in the increasing order of the wavelength we have seen. Types of spectrum. There are two types of basically spectrum obtained. One is emission spectrum, we say. Emission spectrum. Number two, absorption spectrum. Emission spectrum and absorption spectrum. Emission spectrum means the spectrum which is obtained by the emission of radiation from an object, and that emitted radiation when passed through prism, you get a spectrum. That is what emission spectrum. Then absorption spectrum is different. What is absorption spectrum? Let's see. I have taken some gas here in a container. Okay, there is a gas here. What I'm going to do, I'm going to heat this. Heating is like supplying energy to the gas. Okay. Now gas got heated up completely. It has absorbed enough amount of energy. Now the moment when I stop heating, the gas starts emitting radiation. Absorbed energy will be started emitting by the gas because it has absorbed energy. So in order to come back to the normal state, it has to emit absorbed energy. That emitted energy, if it pass through prism, then you get a spectrum. This is called emission spectrum. Okay, emission spectrum. Then what is absorption spectrum? You have to carefully observe now. You have taken gas and heating, right? Gas has absorbed the part of energy that is supplied in the form of heat. Not all the energy will be absorbed by the gas. Entire energy supplied will not be absorbed. A part of energy will be absorbed by the gas. That's all. And the remaining part of heat energy will be transmitted without getting absorbed. That's all. This is transmitted energy. Okay, when you heat a gas or any substance, a part of energy will be absorbed. Remaining part of energy will be transmitted. If you pass these transmitted radiation through prism, then you get a spectrum. This spectrum is called absorption spectrum. Is it okay? Absorption spectrum. Now, the way in which this absorption spectrum and emission spectrum appear is quite interesting. See, absorption spectrum will have kind of like this, you know, it will have bright background like this, and in between there will be dark lines like this. What are these dark lines? Dark lines corresponds to the energy absorbed by the gas. This bright line corresponds to energy emitted. So absorption spectrum generally will have a bright background in between dark lines. Dark lines indicate absence of certain radiation, which is corresponding to the absorption of energy by the gas. Whereas in case of emission spectrum, you know, it is quite reverse. There will be, one second, there will be dark background like this. Okay, in between there will be bright lines. In between there will be bright lines. This is what is emission spectrum. So that's the major difference between this is emission spectrum. This is absorption spectrum. Okay, so these are the two types of spectrum which we need to know. Apart from that, we can also classify spectrum as continuous spectrum. Continuous spectrum means the radiation will be having no wavelength gap. So you can see this is one radiation. Next color will be immediately without any gap. Okay, like this. Next goes with another color, let's say, like this. So that without any wavelength gap, if radiations are arranged, then it is continuous spectrum. If there is no wavelength gap, it is called continuous spectrum. Continuous spectrum. If there is wavelength gap, then it will be called discontinuous spectrum. That's all. Okay. So if there is wavelength gap like this, let's say here one wavelength. After that there is a gap. Next color will be emitted something like this. After that there is a gap now with some wavelengths here like this. Okay, this is called discontinuous spectrum. Okay, so okay, so this is discontinuous spectrum. This sunlight will have all the forms of radiation, so it will give always continuous spectrum. Vib-Gayar is a continuous spectrum. Okay, but whenever you take any element like hydrogen gas also and heat it, the emission spectrum obtained will be discontinuous line emission spectrum. Okay, so that's fine. With this we'll stop with the discussion of spectrum. In the next class we're going to continue with the remaining Bohr's theory and all those things. Hope you have understood. We'll meet for the next class. Till then, take care. Bye bye.
Thank you, sir.
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 Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Yes, I'm going to end the meeting.